welcome to another WJEC A level physics question. This time is question 4 from January 2012's PH4 paper, and it's a gravitation question which is currently in unit 4. And what we start off with is basically the equation for the centripetal force on an object orbiting the Earth and equating that to the gravitational force of attraction of that object to the Earth. And we've got to explain briefly the meaning of each term in the equation. Well, there are two m's, m1 and m2. Now you notice the m2 is here on the right with the centripetal force. So that m2 is the mass of the object in orbit. So this would be the mass of the satellite. And therefore m1 is the mass of the object being orbited. In this case, it's the mass of the Earth. R is the radius of the orbit. And omega is the angular velocity of the satellite in orbit. Next, we've got to use that above relationship to derive an expression for the height of a satellite above the Earth's orbit. H plus RE is cube root of gm1 t squared over 4 pi squared. So let's go back to that original relationship, and you'll notice first of all that we can cancel the m2's. So let's start with g m1 over r squared equals omega squared r. We'll gather the r's together. So we'll get that r cubed will be g m1 over omega squared. But a relationship that we should know for circular motion is that omega is 2 pi over t, where t is the period of the motion. So hence we can write that r cubed is g m1 over 2 pi over t, all squared. R cubed then will be g m1 t squared over 4 pi squared. Dividing by a fraction is the same as multiplying by the reciprocal of the fraction. And because r is h plus re, then we can say that h plus re is the cube root of g m1 t squared over 4 pi squared as required. Next, we're asked to calculate the height of a geostationary satellite above the Earth of mass 6 times 10 to the 24 kilograms with a radius of the Earth of 6.4 times 10 to the 6 meters. So let's plug some numbers into that equation. H plus RE is going to be the cube root of 6.67 times 10 to the minus 11 for G, times the mass of the Earth, 6 times 10 to the 24, times the period of orbit. Now the period of a geostationary satellite is 24 hours, but we need that in seconds, and it's squared all over 4 pi squared. That will give us 42.3 times 10 to the 6 meters, and since the radius of the Earth is 6.4 times 10 to the 6 meters, that will give us h as follows. Which is 35.9 times 10 to the 6 meters. For the final part of the question, we're given that the mass of the satellite is 850 kilograms, and we're asked to find its increase in potential energy when it was initially moved from the Earth's surface to the geostationary orbit. Well, gravitational potential energy is given by minus gm1 m2 over r. So if we want to find a difference in potential energy, we can do minus gm1 m2 over the final position, which is at that radius or height plus the radius of the Earth that we've calculated earlier, and we can take away the initial gravitational potential energy, which is minus gm1 m2 over the radius of the Earth. So let's put those figures in, and by the way, I'm just going to save a little bit of effort by factorising out the G, M1 and M2. So I've got minus 6.67 times 10 to the minus 11 times 6 times 10 to the 24 times 850 times minus 1 over the radius of our orbit, which we worked out earlier was 42.3 times 10 to the 6. Take away 1 over, sorry, add, because of the two negatives, add 1 over 6.4 times 10 to the 6, which is the radius of the Earth. And if we put those into the calculator, we will end up with an answer of 4.51 times 10 to the 10 joules. Thank you very much for listening. Please remember to like and subscribe, and feel free to leave any comments. Goodbye.